Alright, hope everybody's enjoying this delightful cold weather day. I am currently wrapped in a blanket, which is trying to figure out if this is frost on my window or not. I really don't want to poke it in case it is, but you're not here for that. You're here for, in theory, test review, assuming anybody sees this in a timely manner. I'll send an email maybe, or a post. Anyway, test review. So, first thing we got to go on, we got Chapter 6. Chapter 6 is talking all about kind of special models for forces. Should point out these are not special forces, that they are weird and don't obey the laws or anything. They're just specific models of forces. They're not perfect. They're not uniformly applicable, as we have learned every time we've tried to do a lab on them, basically. Really try to work on that or something. But what we're trying to look at are kind of three ways to predict the magnitude of forces in certain situations. And the situations that we're looking at are friction, drag forces, and circular motion. So let's deal with circular motion first, since that's kind of the easiest case. We had said before, in uniform circular motion, there was a required acceleration because velocity is changing, because the direction is changing. The speed stays the same, that's why it's uniform. And we said that there was an acceleration required of v squared over r, and that this was directed radially inward. So, if there's an acceleration, then there must be a force. The weird thing about circular motion, again, is not that by swinging something in a circle you create a force, but rather that a force is required to swing something in a circle. So it's not this way. Swing in circle leads to force. Does not happen. It is that a force is required to swing in a circle. Which seems like, not a circle-y. That doesn't make sense. It's a semantic point maybe, but it's important, and it's kind of a conceptual problem. Like it happens a lot. It is an easy thing to trip yourself up in saying, oh, it's going in a circle, so there is this centripetal force pointing inwards, and this centripetal force is so big, and act like this centripetal force is a force like a tension, like a push, like a pull, like gravity. When in fact what's happening is that some force is supplying a centripetal force. You need to have something supplying this. So gravity could be keeping something going in a circle. This is the case of orbits. A tension could be keeping something going in a circle. This is the case of swinging a rock around your head. Anyway, point is, so this necessary force, this centripetal force, is the force supplying the centripetal acceleration. And so the question you need to ask, kind of the process goes. You see something is going in a circle. And you think, oh, there must be a centripetal force. That's not a question. This is a question. What supplies the centripetal force? This is the big question that kind of underlies these circular motion problems. And so likely candidates, friction is a big one for when you have like a car going around in a circle or something. Tension is a big one for if you're swinging something around. Or the normal force. The normal force is kind of a weird example of this, but consider, if you will, a vertical circle. So for example, you have a motorcyclist, person on a motorcycle, who's clearly wearing a helmet, going around in a vertical circle. So one where, this is not a bird's eye view, it's a head-on view. So the question is, when he's at the top here, oh, this is complicated. And then, again, the helmet. So the person's at the top of the circle, what forces are acting on them? And then when they're at the bottom, what forces are acting on them? So when they're at the top, it's basically gravity and the normal force. At the bottom, normal force. You have gravity. And so when you're looking at this, the lowest force that the faster you go, the easier it is to go around a circle. So there is some minimum speed at which you can go around, and it's set by here. Because one of the things you need to remember about this is that you lose contact with a surface. Lose contact with a surface if Fn equals 0. We talked about this in passing a couple of times, but anyway, just a kind of a random example of that. I think they work it out in the book, but moving on. Let us talk about the drag forces. So, the drag force we had said is basically, it's our model for air resistance. Or more generally, some kind of fluid friction is kind of the way to think of this. If we take an abstract view of friction as any kind of dissipative contact force, then drag forces are basically just when you are encountering not surface to surface interactions, but surface to fluid interaction, remembering that gases are fluids. Kind of. Probably. I really gotta stop saying things that I can't remember properly out of a chemistry course. Anyway, we had two models for a drag force. One that kind of looked like a linear drag force, with the idea being that this minus sign tells us that the direction of the drag force is opposite of the velocity, or quadratic drag force, which if we want to write out, kind of looks like this, so that the magnitude of it looks like something times the square of the speed. This is again so that the direction is opposite the velocity. Your book gives a very specific model for this, one which is not found on the AP exam. And so they say that, the cross-sectional area matters, which makes sense. The bigger the area you present, the greater the drag force. Reasonable. They think that the density of the fluid matters, which makes sense. More fluid, more contact, more drag. And then there is some constant, some situational constant that kind of captures everything else. And you'd basically have to demonstrate that experimentally. There's no easy way to get around that. So the idea is that this whole 1/2 CA rho thing is this constant here. All of these are constant for any given situation. They're just, trying to break apart in terms of parameters what could matter. One thing that we did talk about in the drag forces, and if you go watch the screencast for this, you'll see that sometimes they will ask you to say, all right, write down Newton's second law for a situation where an object falls with a linear drag force, or a drag force that looks like this, and they'll give you a form for it. So this is Newton's second law, right? F net, this is F net, and so F net equals ma. And they want you to write this as a differential equation. And so that means usually doing something like this, and saying that a is the derivative of the velocity. I'm not going to repeat this whole thing because it took a while the first time, and I'm not sure I could do it any better than that. But I will encourage you to go look through that mess of a slog of calculus if you're really interested. It is not the greatest thing to get hung up on. It is reasonably likely that at least this much will appear. It is moderately likely that you will need to solve the differential equation, which gives you something that looks like an exponential something. I'm going to get it wrong if I try to do it off the top of my head. But yeah, the point is is that this leads, so as this gets bigger, because as you fall you speed up, this stays the same, which means that this whole side approaches 0, which gets you this idea of terminal velocity. Terminal velocity is this velocity, I'll call it Vt, such that mg minus bvt is equal to 0. So it's the velocity at which your acceleration equals 0. You stop accelerating, terminal, final velocity. Alright, that is an important thing to take away. Last kind of thing from this chapter was friction. And we said that our simple model for friction would suggest that there is some constant or coefficient of friction which goes against the normal force. And so things that we know, this tells us the magnitude. We know that the direction of friction is perpendicular to Fn. We know that the direction opposes motion. And we know that we have kind of two pictures of this. We have static and we have kinetic. So this is something that is starting to move or trying to move, but not moving yet. And when we look at static friction, we're really getting a max value. And so the idea is that static friction is less than or equal to mu Fn, which is equal to a maximum static friction force. So if you always acted with the same static friction force, you would push something a little bit, static friction would act with this huge value, and the object would fly towards you, which would be awkward. Whereas instead what happens is that it matches up to some maximum value, after which it begins to move, and then the kinetic friction takes over, usually with a different coefficient, and this is acting against something that is then in motion. The homework problem with the block on the wall is good for this. Okay, continuing onwards, we get to Chapter 7. Chapter 7 is really talking about energy in systems with one object. By this I mean we're thinking about an object, which is this wonderful dot, which can have energy, and the only kind of energy that an object can have in and of its own is kinetic, or some. So maybe it has internal energies. The only kind of energies that we care about that are internal is kinetic. In theory, you could have chemical, you could have thermal, based on its temperature, you could have some kind of nuclear energies. Later, other classes. For us, kinetic. Now, this object, which has kinetic energy, can be set upon by forces. There can be things pushing it, pulling it, what have you. All of these forces, these external forces, can do work. And work will change the energy of the object. That is the story that we're trying to tell here. So, when we look at this, we said that kinetic energy will be 1/2 mv squared. One way to think about this is to say, let's see if I can get this right. Nope, can't remember it off the top of my head. There's a clever way to do it. Well, so we know that. Where's the pause button? Nah, whatever. I'll come back to it. There is a clever way to get it, but it's escaping me at the moment. We're going to take as a definition of work that it is force dotted into displacement And so this is this idea of a path integral, which we don't really have to do too often. This is only need to do this for a non-constant force. Your book goes through it talking about a spring force. It's a good thing to look at and to kind of get the picture of how it flows out. For a constant force, though, what we're basically looking at is force dotted into displacement. Just good old-fashioned displacement. It goes from here to there in something resembling a straight line. And that will tell us the work done by a given force. You'll note this is the dot product. Way back from chapter 3, it makes a wonderful return, which means that the work done is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them, which tells us this wonderful thing that if F is perpendicular to displacement, then there's no work. Which is why if you carry something, yeah, that's not exactly true, but if you carry something at constant velocity, you do no work. Awkward. I know. Alright. If we look at this, we could take as some examples the work done by gravity. We can look at the work done by a spring. All of these are kind of useful things. And they work them out in specific cases. The general idea that we're coming down to is this law of conservation of energy, or the first law of thermodynamics. First law of thermodynamics basically says that the change in energy of our system, which right now is just changing kinetic energy, is equal to the work. It's the only kind of energy we have, and so that's all that can do. This is what we're calling in your book the work kinetic energy theorem. The reason we kind of blew through this stuff is because usually we want to start talking about other kinds of energy than just kinetic. We want to talk about potential energy. So we take these works and we turn them into potential energy. Which would be helpful if I could spell. And this is what happens in chapter 8. But for now we're looking at kind of saying, alright, we have a force, it does work on an object that changes the energy of the object, so the object's going faster or slower. Positive work means a positive change in kinetic energy. So positive work done on an object means that the object's speed increases. You can see that kind of the sign of this comes out of this cosine. So if the force and displacement are in the same direction, so theta is between 0 and 90, I just made a wonderful motion with my hand that isn't captured, then the cosine is positive, work is positive. So if the force is in the direction of motion, work is positive. If the angle is between 90 and 180 degrees, basically, or 90 and 270, sorry, if it's a 180, swing from there. Similar if it's between 270 and 90, but whatever. I digress. If the force and the displacement are in opposite directions, you get a negative work. It slows it down. So if you're pushing something in the direction of motion, it speeds up. Pushing something in the opposite direction of motion slows down. Which, shockingly enough, I think makes sense in most cases. Right. One other thing was power, which we can think of best as the rate at which work is done. So the average power, just like the average velocity is how fast you go, or how far you went over how long it took you. The average power is kind of the work done over the time. There's nothing weird about this. This is the work, this is the time, there's no calculus, there's nothing odd. The instantaneous power, then, would be kind of the time derivative of the work. It always feels weird looking at that to me, but that is the rate at which work is done should be the rate at which... Yeah, it should be. I don't know. It bothers me for some reason, but it shouldn't be an issue. So don't think too much about that. Lastly, we get to the bit of chapter 8, which is important. So in chapter blah blah blah. Chapter 7, we were saying that the change in kinetic energy was equal to the work, and we could say that the work came from such sources maybe as gravity, as some spring force. Maybe there's some work done by friction. Who knows what other things. The idea is that some of these forces that act are going to be what we call conservative forces. Conservative forces, also known as path-independent forces. Not, yeah, never mind, that's probably a bad joke to make. Oh god. I can't remember if it's ent or ant. Ent looks better to me right now. Alright. What this means is that the work done only depends on the initial and final states. So what this means, if I compress a spring and expand and let it expand and stretch it and compress it and stretch it and compress it, at the end of the day, all of the stretching and compressing doesn't matter in terms of what my final results will be. If it started compressed and ended expanded, that will be the same no matter how much goes on in the middle. Same idea as if I bring something up, drop it, bring it up, drop it, bring it up, drop it. Whatever the final change in its distance is, if it starts 10 meters up, ends 1 meter up, it doesn't matter if it goes up and down in the middle in terms of what its speed will be, unless there's some other forces acting on it, pushing it up or down, in which case that changes things. But in terms of its energy, as related to gravity, as related to the spring, all it cares is what the configuration is. So that means we have kind of two sets of work. We have work from conservative stuff, and we can have work from non-conservative stuff. So friction cares about the path you take. The bigger the path you take, the more friction you accrue, the more work it does. It very much matters if when going from A to B, you go by the straight line or you go by some more squiggly lines. There can be significantly more effort involved. The idea would be, by the way, if you're going up, and if this is gravity, here there's no change in gravitational potential energy on the straight line. Here, you have to do work against gravity, going up, but coming down, gravity does work. That's the idea. Anyway, the idea is that these conservative forces can be we can think of them in terms of, an initial and final state, just like we can think of the kinetic energy in initial and final state. So where we have, this minus mgh, and instead of h, we can think of it kind of as a delta y, a change in height. We have this minus 1/2 k, the change in extension. That's an initial and a final again, plus whatever dissipative works we want. We can think, instead of moving these over to the other side of the equation, so we have delta k plus mg delta y plus 1/2 k delta x squared. And now this we think of instead as a potential energy, we say. Just a change of label. So collectively, we call this our mechanical energy. And we have another statement of our idea of conservation of energy, where we have these three major types that we play with: kinetic, gravitational potential, elastic potential. These potential energies are, involve two things. Involves our object and some external force, some external agent. In the case of gravity, it's the earth. Gravity is acting. In the case of a spring, it's a spring, an elastic force that's acting. Yeah. Okay. I hope that wasn't too rambly. But this is, content-wise, what we're covering. I will try to do another one of these in a bit that has a couple of problems worked out, but I need to find a textbook in order to do that. Good luck.